Hey guys, I was looking at the videos in my channel, and I saw that I don't have a lot of simple harmonic motion videos. I don't know why, since that is the one topic which you can find in many physics classes. Be that as it may, let's get right to it. This example says, a particle executes simple harmonic motion with an amplitude of 3.43 centimeters. At what positive displacement from the midpoint of its motion does its speed equal 1/2 of its maximum speed? Answer in units of centimeters. So as you can see, we don't have a lot to work with. Well, at least not a lot of numbers, but we have some information. So let's start with the given. And then we have a relationship between the speed that they want and the maximum speed, which is as follows. And then, because they want positive displacement, what they want to know is the value for x, and I'll explain why x. Okay, so what do we do here? Well, let's start with the few formulas that we're going to need. Because we have a particle undergoing simple harmonic motion, we can model this particle as if it were a mass on a spring. Let me show. This simulation, it's from PhET. Okay, so I'm going to play slow motion. This line is the equilibrium line, okay? So if we were to let this run, and let's say we had we had normal damping. Eventually this spring will come to a stop and it would be here. Kind of like a pendulum when it's at its bottom position before you move it. It would just be resting here. But because I have no damping, it'll just go. And that's what's happening. So we're going to model this particle as a harmonic oscillator. Well, we know that this mass on a spring, the harmonic oscillator, has a potential energy of 1/2 k x squared, where x is the displacement. So there's the displacement that we want. And I know k is the spring constant, but of course for a particle, it doesn't have a spring, so we have to think of that k term in a different way. All right, so the one thing about harmonic oscillators is they have cyclical motion, right? The motion repeats. It's the same forever, right? Because this one has no damping. So this spring will go on until I stop it. So now what I want to show is, what if we were to graph the motion, right? What if we were to graph the motion? So this is simple harmonic motion, and as you can see, we're tracing a wave, and that is not any wave, it's a sinusoidal wave. Okay, for those of you taking pre-cal, you know what that means. And the way I want to model this one is with something we have learned in the past, circular motion. As you can see, we have the wave over here, and let's say we wanted to find out how fast this was moving, okay? Let's see, we want to find out how fast this was moving. Well, we can use the formula for angular velocity, angular speed, and we use the Greek letter omega. To make a distinction between the regular angular velocity we learned in Unit 5 and this one, I'm going to say omega naught, okay? That's simply how fast we complete one cycle. And we know one cycle, right, when the wave starts over, we complete one full rotation. So the angular displacement would be 2 pi. And how do we know the time? Well, the time for this object, right, this is simple harmonic motion. This is based on the mass on a spring. The time it takes to complete one cycle, it's called the period. And we know that period, we use the letter T. Okay? Furthermore, we know what the period of a mass in a spring is. We know that the period is going to be 2 pi times the square root of m over k. So now what I'm going to do is I'm going to plug this one in here, and we'll have 2 pi over 2 pi times the square root of m over k. Notice how the 2 pi's are going to cancel. And now I can rewrite this omega naught as 1 over the square root of m over k. And that I can rewrite by flipping the radicand. And I'll get that omega naught is equal to the square root of k over m. This formula, guys, is very, very important, okay? Very important. It has a special name. We're not going to call it angular velocity or angular speed. This is the formula for angular frequency, okay? Formula for angular frequency. You should write it down. So now we can use this relationship with our potential energy, okay? Because this K here is no longer the spring constant, but it's a property of the harmonic oscillator. So we're going to use this in this formula. We're going to substitute, okay? But before we do that, let's solve for K. Let's solve for K. That's easy. We square both sides. And then we multiply times the mass. And this value for K, I don't want to go into what it means. It's beyond the scope of this class. But it's equal to the angular frequency squared times the mass, okay, for this particle. So now we can say that the potential energy is equal to 1/2. Instead of K, I'm going to have omega naught squared m times x squared. Okay. So far, so good. Now what do we do? Let's go back to the simulation. Let's think of things in terms of energy, okay? So the total energy, right, the total energy we have over here, we have to think of, we get the maximum energy, or the total energy is at its maximum, when all of it is potential energy, okay? And when did this happen? Well, let's look at the motion of this mass on a spring. We get the maximum potential energy when we have the greatest displacement, right? When the spring is either stretched or contracted, compressed at its maximum. Okay? Again, the maximum potential energy happens when the displacement is at its maximum. So we can say that the total energy, as shown over here, right, it's potential energy, but it's potential energy when the displacement is at its maximum. And for that one, let's use the letter A, because that's the maximum, that's the amplitude, and that number we do have, okay? Again, so we don't forget, let's say this is the maximum displacement. Okay, now what do we do? Well, we can apply conservation of energy, because the total energy is simply the kinetic energy of the particle plus the potential energy of the particle, which will look as follows. But we have all these equations. We have all these equations. Let me move this so we have room. So the total energy is 1/2 omega naught squared m a squared. That's equal to the kinetic energy, and that's simple. It's just the normal kinetic energy, 1/2 m v squared plus the potential energy at any other point that is not maximum displacement, so 1/2 omega naught squared mx squared. Okay. And we can cancel a lot of stuff. All right. And I'm not going to go into why this is the case, but the maximum speed of this oscillator, let's call it Vmax, is simply the angular frequency times the amplitude of the harmonic oscillator. And we were given a relationship that the velocity we are looking for, the velocity we're using, is half its maximum speed, okay? What that means is the velocity as we were given, which is 1/2 Vmax, we're going to use this equation here. We're going to say that V is equal to 1/2 angular frequency times amplitude. And now we'll use this here, because when we apply this velocity, then we can solve for this displacement, which will give us the number required to reach this velocity, which is the one we want, half the maximum speed. Okay, so now let's plug that in. Okay, now let's clean this up. Don't forget that the square will go into everything that's inside the parentheses. And now we can get rid of omega naught squared, of the angular frequency squared. And now that you solve for x. Okay, and we have a squared minus 1/4 a squared, so it's just fractions, nothing we haven't seen before. Don't forget, next to this a squared, there's our 1, and I make 1 into a fraction with a denominator of 4, so it's 4/4. So then x squared is simply 3/4 a squared. We take the square root and we end up with x is equal to plus or minus, equal to plus or minus, that's very important, okay, plus or minus the square root of 3/4 times a. And we can take the square root of 4. So just to make this slightly more elegant, I'm going to work to the left and change color just so you see that's going to be the answer. So x is going to be equal to plus or minus the square root of 3 divided by 2, because the square root of 4 is 2, times a. Because they want the maximum positive displacement, or I don't know if they say maximum, but they want the positive displacement, we'll just do the positive version of this. So the displacement that they want is going to be, which is the amplitude we were given in the problem. So now we just get square root of 3. Now make sure the division sign is not part of the square root, times 3.43. And there you go. So our answer is 2.97 centimeters. And that's it.